programming. And up till now, there are still some other programs, businesses, companies that are making use of linear programming. So, starting from the first person in my group, Gabriel Samson Okona, the outline of the content, definition of symmetric primal dual pair, writing the dual of a general primal LP with duality theorem, simplex, multipliers, solve the dual, economic interpretation of dual LP, fundamental duality theorem, Farkas lemma, complementary slackness. There are actually a lot of subtopics inside the linear programming. But if we understand the basis of linear programming, it will be very easy for we to go through the whole lot of pages here. And when we talk about duality in linear programming, the words we'll be using will be primal, dual, and also variables, objectives, functions. So these are the keywords we'll be using. But the thing is, you have to have a picture of what we'll be talking about. Let's assume this is a shirt. And we also have another shirt here, but a less smaller one. Very good. So, when we talk about duality, it has to do with something having two bodies or in two states. And when we talk about primal, it has to do with something original and single. So, taking it to these two diagrams, we will say this is primal. And we will say this is dual. Why do we call primal? We will say this is the original, and this is a second pattern of this particular thing. So right now, before we begin to explain about this, you see, primal, minimize CTX, subject to AX greater than B, X greater than equals to 0. Then in the dual, you will see maximize B, T, Y, subject to ATY less than C, Y greater than equals to. So what is the difference? From the very beginning, or maybe from that diagram, you'll be able to see that we have a bigger shirt and a smaller shirt. So now, when we say CTX, when we say minimize CTX, subject to AX greater than equals to B and X greater than equals to 0. This is a mathematical expression, and this mathematical expression means that what we have here is called the objective expression. Then subject to AX greater than B. What we have here are AX and BX. And this particular one including, these are called constraints. So these two are called constraints. In this objective expression, we have a variable x. And the main idea is to either minimize the variable or to maximize it. So, bringing into the two sheds here now, prima is we already have something big, but the idea is we should make it, we should minimize it. We should minimize it, but the essence is that it should not be greater than or equals to this. We cannot make it bigger than this, but it should be less than equals to this. Then the twelve is to maximize it. So we cannot have less than or equals to. We cannot have it less than this. We should at least make it bigger than this, or we should leave it at this particular point. So for every primal solution, it should be greater than equals to. Then for every dual solution, it should be maximized with less than equals to. So this, we call them the non-negative inequalities. So this we call the non-negative inequalities. So once we go further, we'll be able to see some possessing two different things in primal and also in duality. It is also stated here that A is a maximum matrix. X and C are vectors of length n, and Y and B are vectors of length m. Then the AT denotes transpose of the matrix. The primal LP is maximum, n constraints, not including non-negativity, and n variables. The dual linear program is minimum, that is n constraints, not including non-negative and n variables. So it's the same thing I was saying here, that for every primal, it is to minimize. Then for every dual, is to maximize. Then another note for the expression. Say for every variable in the primal problem, there is a corresponding inequality constraint in the dual problem. For every inequality constraint, not including non-negativity, there is a corresponding dual variable. This is like a transpose of the former equation. Like we see here, we have the objective expression is to minimize CTX. But it is the CTX, which is the objective expression, becomes a non-inequality in our dual problem, which is the C here. And going further, we will see, to make it more clear, it says the right-hand side vector B, which is this particular one, of the primal problem, this particular one in the primal problem, serves as the objective function, coefficient vector of the dual problem. Now, we have the vector B in the primal problem, but it is the objective function now in the maximized BTY. Assuming we have something like this, probably minimize I want to use other letters so that you will understand what I'm saying. M MTX, then subject to, let's say, B plus A greater than equals to let's say D. So if we have something like this, minimize MTX subject to B plus A greater than equals to do. In the dual problem, how will it look like? In the dual problem now, this function now will become the objective function in the dual problem, which will now be maximize dtx. So it will now be maximize dtx. So this will be b less than equals to m. So the m now will now change formation here, and this d now will replace the mt in the dual problem. So it's something changing of formation. That is how it looks like. So if you see the demonstration, they said the b, which is one of the constraints, is now the objective function in the dual maximization. Then the objective function in the primal, which is the CT, is now the constraint in the dual maximization process. Another example here is we have a primal problem of to maximize 20x1 plus 10x2, then subject to 5x1 plus x2 greater than equals to 6. We have 2x1 plus 2x2 greater than or equals to 8. And the constraints here are x1 should be greater than or equals to 0. x2 greater than equals to 0. So now, how does this look in the dual problem? In the dual problem now, our constraints are now the objective function in the dual problem, of which we are to maximize. Here we have a constraint of greater than equals to 6, greater than equals to 8. And once you check the objective function for the dual problem, you have them as the objective function being 6y1 plus 8y2. And also, the objective function in the primal problem, which is maximize 20x1 plus 10x2, is now the constraint in the dual problem, which are less than equals to 20 and less than equals to 10. So it's just changing of formation. Then another key thing from here is in the primal and the dual problem, it is compulsory that the constraints in the primal must have a greater than equals to signs in their inequalities. And also, for the dual, they must possess a less than equals to signs in the problem. So here is another key fact I want to point out. They said the primal problem is a minimization with greater than equals to constraints, while the dual problem is a maximization with less than equal to constraint. So if you set the minimization, which is the primal, you have greater than equals to signs, and if you set the dual, you have less than equals to signs. And that is compulsory. You must have them for the problem. Like the same thing I've been saying, the inequalities for the primal are the objective functions in the dual problem.
Representing. Sorry.
They understand what God is.
So, one more last thing before I conclude.
Before conclusion,
Please, one house.
before conclusion, okay.
Filming. So before I conclude with we've already known how duality is like. We must have an objective function, we must have constraints, and we must have inequalities. But in a situation whereby our inequalities are not real inequalities, for example, something like 5x1 plus 2x2 is less than equals to 4. And our second inequality will be something like 4x1 plus 3x2 greater than equals to 5. And we are trying to minimize, let's say, b 5x plus 2x. So, when we are trying to minimize something like this, we can see that our inequalities are not the same. Once we don't have them the same, greater than equals to, less than equals to, we have to try to make all of them the same. And by doing that, we multiply this particular one with 1, minus 1. So once we multiply it with minus 1, we change it to 2 formations. Either minus 5x1 plus 2x2 greater than equals to minus 5. So we've changed the inequality to the down one. So these are the key things. Once you don't have the inequality, you change the inequality and you use a simplex method. To solve it. So the essence is minus. So the essence is to minimize cost and also to maximize profit. Thank you very much for your attention.